Hello વિદ્યાર્થી મિત્રો, આપણે ચેપ્ટર નંબર 1 રિલેશન ફંક્શન્સમાં 1 to 6 યુનિટ્સ લેક્ચર આપણે કરી ગયા છે. લેક્ચર્સ આજે આપણે 7th લેક્ચર લઈએ. Lecture number 7. Number 7. This one is nothing but illustration number 16. Find g of an approach if f is from R to R, g from R to R, given by x is equal to cos x and gx is equal to 3x. Let us recall the definition of composition of two functions. If f is function from a to b and g is function from b to c. If or c2, let us consider c2. In general, let us define it. C2b. If range of g is subset of domain f, then f of g is defined and is function from domain of g to codomain of f. Okay. And if range of f is subset of domain of g, then g1 composition of g and f is defined. Is function from where to where domain of f, that is a, to codomain of g, that is p. Here, in this way we can see the compositions. Here, so let us see here. F is from R to R is given by f is equal to cos x, and g is also from R to R. G of x is equal to 3x square. Now here also see that range of f is subset of R, range of f is subset of R, and that is equal to domain of g, and range of g is also subset of R, and that is equal to domain of f. And therefore f of g and g of f are both defined, and where is from? F of g is from R to R, and g of f is also from R to R. There. Let us see. Okay. Now, for all x belongs to R, f of g at x is equal to what? That is equal to f of g of x. What is g of x is given here? See, g of x is 3x square. So that is here is equal to f of 3x square. Here. Now f of x is equal to cos of x. F of y is equal to cos y. So f of 3x square is equal to cos 3x. Cell number 1. Also, for all x belongs to R, what is g of f at x is equal to g of f of x. Now see here, what is f(x)? F of x is equal to cos x. So that is equal to g of cos x. Okay. Now you can see here, here g of x is equal to 3x square. So g of some value, that is equal to 3 times some value square. So what happens here? See here, that is equal to 3 by 1 into f4 g at x is not equal to g of at x, and this one is true for all x belongs to R, and therefore f4 g is not equal to g of x, and that thing we want to see here. See here, f is from find f of g and g of x, so that f of g is not equal to g of x. That we want to see, and that thing already seen. Clear? Now see here. Next, see, that is illustration number 7. Illustration number 7. Now see, f is given from where to where? R minus 7 by 2, R minus 3 by 5. That is the domain of f. And this one is codomain of G, codomain of F, sorry, and is defined by this way. Why we are separating 7 by 5? Because for at x is equal to 7 by 5, this quantity is 0, so that we have to remove from the domain. Same way, this one is domain of G, and this one is codomain of G, and this is given by 5x, 7x plus 4 over 5x minus 3. X should be not equal to 3 by 5. Clear? Now here we are calling that A is equal to this one, B is equal to this one. Now I at x for all x belongs to A, I B at x for all x belongs to B are for identity function on set and B respectively. Clear? Now we want to prove this thing. Now let us see one definition. If for function from A to B that exists function g from B to A such that f for g is equal to identity function on domain of G, and g of f is equal to identity function on domain of A, then g from B to A is called inverse of f from A to B. So this is the definition of inverse function. Now here what we want to see, the f of g is equal to I and g of f is equal to I. Clear? So let us see that. Now see. Here A is equal to R minus 3 by 7, sorry, 3 by 5. See, A is equal to R minus 3 by 5 and B is equal to R minus 7 by 5. That is given to us here. See, now F is function from where to where? Here to here. So range of F is subset of domain of range of F is subset of A. Subset of A, and range of G is subset of B, and therefore range of F is subset of A is nothing but is domain of G, and range of G is subset of B. Range of G is subset of B, and that is equal to domain of A. And therefore F of G and G of A are all defined. Clear? And F of G is function from domain of G. Domain of G, that is A to codomain of A, that is also A, and G of A is function from where to where? Domain of A, that is B, to codomain of G. What is codomain of G? That is B. Clear? So this is the existence of composition. Let us 1 minute write here. What is fx? Fx is equal to 3x plus 4 over 5x minus 7. And what is gx? Gx is equal to 7x plus 4 over 5x minus 3. Now our aim is to see f of g is equal to, for all x belongs to A. Why? Domain of F of G is A. So we have to start with all element belongs to A. F of G of Fx is equal to F of G of X. What is G of X? G of X is 7x plus 4. F of 7x plus 4 over 5x minus 3. Clear? Now that is equal to, let us see here, f of x is equal to 3x plus 4 over 5x minus 4. If you take here y, then here y. If you take here sum any form, then here 3 times something over 5 times something. Clear? So let us see here, that is equal to what happens? F of, that is 3r, 3x plus 4 over 5x minus 7 plus 4 over 5 times 3x plus 4. See, that is f of 3x plus 4 over 5x minus 7 Here, that is f of x. We are using this part here. So now take LCM 5x minus 7 from numerator and denominator quantity, and then simplify what to get here. 3 3s are 9x plus 12 plus 5 4s are 20x minus 28 over 5 3s are 15x plus 20 minus 35x minus plus 49. See, that is the domain of A and G. Clear? So what we get here? Here what we get? 9x plus 3r. Gx is equal to, sorry, here we have to take this thing here in place of this one. So let us see here. See, what do we have to see? F of something is equal to 3 times 7x plus 4 over 5x minus 3 plus 4 over 5 times 7x plus 4 over 5x minus 3 minus 7. Clear? See here. So that is equal to 21x plus 12 plus 20x minus 1 over 7 5s are 35x plus 20 minus 35x plus 21. Now 12 will get cancelled. that is here 41x over 35 cancel 41. That is equal to x. And we can write that as equal to IA at x. So what we prove? For all x belongs to A, FOG at x is equal to IA at x. And this one is for all x belongs to A. And therefore FOG is equal to IA. Everyone to prove. Same time, let us see here. For all x belongs to B, here g of f at x is equal to g of f of x, and that is equal to g of what is fx. Fx is nothing but 3x plus 4 over 5x minus 7. And that is equal to, see, and that is equal to g of something. See here, g of something is equal to 7 times something plus 4, 5 times something minus 3. So here that is equal to g of something, that is 7 times 3x plus 4 over 5x minus 3 plus 4 over 5 times 3x plus 4 minus 7 here. Here 7, 3x plus 4 over 5x minus 7 minus 3. Now take LCM. What we get here? 21x plus 28 plus 20x minus 28. Same way here, 15x plus 20 minus 15x plus 21. So what we get here? 41x over 41, and that is equal to x. And that is equal to, we can write identity function IB at x, because we are taking x belongs to B. So what we seen, and therefore for all x belongs to B, g of f g of f at x is equal to IB at x, and this is true for all x belongs to B, and therefore g of f is equal to IB. Now let us see that thing we want to prove here. See what we want to show here. We want to show that f of g is equal to IA, f of g is equal to IA, and g of f is equal to IB. In that case, g from B to A is called inverse of f from A to B also. Clear? So g of f is equal to this one. So let us put in not here g from A to B, g from where to where? G from A to A, A to A, A to B, sorry, G from A to B. A to B is an inverse of F from B to A here. Clear? Now let us see next. Now see. See here. Very important thing. Here so that F from A to B and G from B to are onto, then G of F is also onto. That thing we want to prove here. Now see, let us define definition of onto function. F from A to B function is given to us. If range of F is equal to B is nothing but codomain, then function is onto. Or in other words, for all y belongs to B. That means every element of B should be image of some and some element of domain. For every y belongs to B, there exists x belongs to A such that f of x is equal to y. That means for all y in codomain, there should be some element in domain such that f of x is equal to y. Then f is called onto function. Clear? We already seen exercise 1.3. Now here we want to show that GOF is also onto. GOF is also onto. Now let us see. For every y belongs to C, for every y belongs to C, G from B to C is onto, and therefore we have some B belongs to B such that G of B is equal to C. Sorry, G of B is equal to Y. Is equal to y. Now B belongs to B, that is in codomain of F, and F is onto, and F from A to B is onto, and therefore we have x belongs to A such that, as per this definition, such that f of x is equal to b. Now replace this value of b here, and therefore g of b is equal to y implies g of f of x is equal to y implies GOF at x is equal to y, and therefore for every y belongs to C, we have x belongs to A such that g of f at x is equal to y. So every y in C, we have some x is in A such that g of x is equal to y, and therefore GOF from A to C is onto. Clear? Now let us see next example. See here. Here f and g such that GOF is defined and is 1 1. Are f and g both are necessarily 1 1 is nothing but very simple example, and is a illustration number 20. Illustration number 20. So let us leave for homework. Next, see, are f and g both necessarily onto? If GOF is onto, is illustration number 21. So let us leave for you homework. Next, now see. Next, let us see this thing. This example here, f from 1, 2, 3 to ABC, B, 1, 1 and on to functions given by this one. So that there exists a function g from B to A such that GOP is equal to I and FOG is equal to I, where x and y is this one. That means we want to see that this one is inverse like a previous sum. Now see here, f is from A to B. f of 1 is equal to A, f of 2 is equal to B, and f of 3 is equal to C, and therefore it is 1, 1 and 1, 2. And it is given also, and f is equal to what? 1A, 2B, 3C. Now show that there exists a function g from ABC to this thing. Here x and y, not A and B. X and y. Now define g from y to x by reverse process. See, define g of A is equal to 1, g of B is equal to 2, g of C is equal to 3. Clear? G of A is equal to 1, g of B is equal to 2, g of C is equal to 3, and g is also 1, 1 and 1, 2. 1 minute. What mean by 1, 1ness? So for all x1, x2 belongs to A, x1 not equal to x2 implies fx1 not equal to fx2. Then function is 1, 1. In other words, for some x1, x2 belongs to A, f of x1 is equal to f of x2 implies x1 is equal to x2. Then it is also 1, 1. Clear? And all is seen. Now you can see that here. See. G of A is equal to 1, G of B is equal to 1, G of C is equal to 1. Every distinct element has distinct images. So it is 1, 1 and 1, 2. Now let us see next what we want to show. We want to show that f of g graph is from Ix and f of g is equal to Iy. Now see here. Now g of f. Where is graph from where to where? Graph is from domain of g of f from domain of f to codomain of G, and f of G is function from domain of G to codomain of f, that is y to y. And therefore for all x belongs to means x is equal to nothing but, see, what is x? 1, 2, 3. 1, 2, 3, and what is y here? Already seen that. So for all x belongs to in this way 1, 2, 3, or we can take one by one image also. Now see, g of f at 1 is equal to g of f of 1. What is f of 1? F of 1 is a. G of a. What is g of a? 1. Same way, GOP at 2 is equal to g of f of 2. What is f of 2? B. So that is g of b. And what is g of b? G of b is 2. And what is GOP at 3? GOP at 3 is equal to g of f of 3. What is f of 3? C. That is g of c. And what is g of c? That is 3. So 1 to 1, 2 to 2, 3 to 3. So we can write here, therefore g of at x is equal to ix at x for all x belongs to x. And therefore GOP is equal to ix. Here. Next, what we want to see? We want to see FOG. Now, FOG at A is equal to f of g of a. And what is g of a? G of a is 1. So, f of 1. And what is f of 1? That is a. Same way, FOG at B is equal to f of g of B. And what is g of B? 2. And what is f of 2? B. FOG at C is equal to f of g of C. G of C. What is g of C? 3, and that is also 3. So, A to A, B to B, C to C. So, we can write for all x belongs to y, g of, FOG at x is equal to IY at x. And therefore, FOG is equal to IY. See, this is the proof of this example. What we want to see here, here we want to show that for this function FOG is equal to IY and G of F is equal to IX. So here we can say that G is also inverse. See, that is extra part. Here G from where to where? G from y to x. Y to x is inverse of f from x to y is also here. Now next, see here. Next, that is given to us in this way. Now let us see. F from n to y be a function defined as fx is equal to 4x plus 3, where y is given to us. So that f is invertible, find the inverse. Now see, if f from a to b there exists g from b to a such that FOG is equal to identity function of domain of G and GOP is equal to identity function of domain of A, then f is said to be invertible function. That means inverse of function exists, and G from B to A is called an inverse. Clear? See, in this way here we have to see that thing. Now see, here f from n to y, f of x is equal to 4x plus 3, where y is nothing but y belongs to n such that y is equal to 4x plus 3 for some x belongs to n. That is given to us. Clear? Now take f of x is equal to y. So for y belongs to y. So therefore 4x plus 3 is equal to y, and therefore 4x is equal to y minus 3, and therefore x is equal to y minus 3 by 4. X is equal to y minus 3 by 4. So here we can define function g. Define g from, see, there is f is from n to 1. So what we have to define? G from y to n by 0 y is equal to y minus 3 by 4. Now f is from n to y and g is from y to n. Clear? This implies range of f is subset of y. Subset of y. That is domain of g, and range of g is subset of n, and that is equal to domain of f. And therefore f of g and g of f are both defined. And where is f of g from where to where? Domain of g. Domain of g to codomain of f, and g of f is from where to where? Domain of f to codomain of f. Here? Yes. Now let us see. Let us not make that fx is equal to fx is equal to 4x plus 3. And 0 of y is equal to y minus 3 by 4. Now see. Now arrange to see that thing. And therefore, for every y belongs to y, f of g at y is equal to f of g of y. What is g of y? That is f of y minus 3 by 4. And what is f of, see, f of x is equal to 4x plus 3. What here x, so here x. If here y, then here y. Here something, so here something. Clear? So that is equal to 4 times y minus 3 by 4 plus 3. That is equal to y minus 3 plus 3 is equal to y, and that is equal to iy of y. So what we see? And therefore for all y belongs to y, f of g and y is equal to iy and y, and therefore f of g is equal to iy. Similarly, what we will see? For all x belongs to n. Why? Because n to n. 0 f of x is equal to 0 f of x. What is f x? 0 4x plus 3. Now g of y is equal to y minus 3 by 4. That is equal to 4x plus 3 minus 3 by 4. That is equal to x. that is equal to identity fx. So what we see? Identity on n. Identity on n. So for all x belongs to for all x belongs to n, g1 f at x is equal to I at x, and therefore log is equal to I n here. And therefore we can say that f from n to 1 is an invertible. And inverse of f from n to y is g from y to n, 0 y is equal to, yes, y minus 3 by 4. Yes, see, in this way we can find inverse of function. Next slide. See, y is given from n square, n belongs to a subset of n. F from n to n is equal to n square, so that is invertible. Find inverse. Here, f from n to 1, f from n is equal to n square. And therefore what happens? See here and see, and y is equal to n square. N belongs to n. It is a subset of n is given to us, and therefore f of x is equal to fx is equal to y implies what is fx? So x square is equal to y implies x is equal to root y. We can take it because x and y both are in n. See, both are in n. So define g from y to n by g of y is equal to root y. Now as per previous example, we have to show that f of g and g of f. Clear? Now let us see. See, here, range of G is subset of n, and that is equal to domain of F, and range of F is subset of Y is equal to domain of G. Clear? And therefore f of G and G of F are both defined. And where to where? And f of G is from where to where? Domain of G. What is domain of G? Y. To co-domain of F, that is Y. And GOF is from where to where? Domain of F, that is n to n. Clear? Yes? Now for all y belongs to y, f of g at y, that is equal to f of g of y. What is g of y here? G of y is root y, and that is equal to f of n is equal to n square, and so that is equal to y, and so we can write that is equal to iy of y, and therefore for every y belongs to y, f of g at y is equal to identity function on y. and therefore f of g is equal to iy. Now we want to see that g of f. So for all x belongs to n, GOP at x is equal to g of f of x, and that is equal to g of x square, and that is equal to root x square, and that is equal to x because of x is in n. So that is equal to identity function on n. So what we seen, for every x belongs to n, GOP at x is equal to identity function on x, and so g of f is equal to identity function on f. So this one is invertible function, and therefore f from where to where, n to y, is an invertible function, and its inverse is g from y to n, g of y is equal to root y. So in this way we can see that thing. So dear friends, let us see next example. See here, very important thing. Here function f is defined by fx is equal to 4x square plus 12x plus 15. Clear? So that f from n to s, where s is the range of f, is invertible, and find the inverse of f. On same line we have to see here. Here in not f dash, but it is f. Here notation my f dash is given to us. Here f is from n to r. F of x is equal to 4x square plus 12x plus 15. Now most important things here. Let us see. See, that is equal to, sorry, this not visible, same color. See, make it a perfect square. 4x square plus 12x. So this one is 2x whole square, 2x whole square. So here we need to add 9. So if we take 2x plus 3 whole square, then 4x square, 3 to the 6 plus 12x plus this thing. Clear? So make it into the perfect square form. Plus yes 6, so that is 2x plus 3 whole square plus 6, yes or no? Now for n to s, now for f of x is equal to y, what we get? 2x plus 3 whole square plus 6 is equal to y, and therefore 2x plus 3 whole square is equal to y minus 6. Clear? Now see here. See, 2x plus 3 whole square is greater than or equal to 0, implies y minus 6 greater than or equal to 0, implies y is greater than or equal to 6. Y is greater than or equal to 6. That means function n to r is given to us, but f from n to s, if we take it, then what is the range? And therefore f from n to s is f of x is equal to 2x plus 3 whole square plus 6. Where what is s is nothing but 6 to infinity. See here, greater than or equal to 0. Clear? Now see, if we take positive integers, n is integers, then if we substitute here, then we get integer only. So here we can, in place of this thing, we can write s is equal to n greater than or equal to 6 and belongs to n. See, clear? Yes. Now let us see. Now see, this implies 2x plus 3 is equal to root y minus 6. This implies 2x. This implies 2x is equal to root y minus 6 minus 3. This implies x is equal to root y minus 6 by 2. So define g. G from where to where? S to n by g of y is equal to root y minus 6 minus 3 by 2. Now dear friends, rest of thing is for you. Check for f of g and g of f like as previous example, and then try to see f of g is equal to is and g of f is equal to in. Clear? Then g is inverse of this function. Dear friends, today we are going to see up to this stage. Next time we are going to see more things. See, in homework sum, same sums, whatever may be classwork sums, that for you. Clear? Thank you.